So this video deals with solubility of slightly soluble salts. You really need to review the solubility rules. You're going to need to know them. And you need to review slightly soluble salts from Chem 105, because this problem I'm going to solve right now is related to that. It's just a little bit more complicated. So my question is, what is the solubility of lead sulfate in a 0.0100 molar solution of sodium sulfate? So what we have to recognize here is I have two chemicals that I'm throwing in water, the lead sulfate and the sodium sulfate, and they're both going to react. The lead sulfate is straightforward. Both of them are straightforward. The lead sulfate is slightly soluble, and so we get +2, lead +2 plus sulfate -2 in equilibrium. And this is a nice table because it's in equilibrium. The other compound, the sodium sulfate, also reacts, but you have to understand that it's soluble salt. How do I know? Because it has a 1A element, sodium, in it. That means it's going to be 100% soluble. So when I react this, it's a one-way arrow, and I get 2 sodium pluses plus SO4 -2. And this is an if table, and it reacts. Initially, I have 0.100 molar, 0 and 0. When I'm done, I have 0 final, 0.2 molar, and 0.100 molar here. Okay, so now I use my concentration of sulfate, goes in here as an initial amount, goes right over here. Okay, so initially I have, since it's a solid, an infinite supply, 0 and 0.100, and the change is always -x plus x plus x dash for an infinite supply, x and 0.100 plus x. So I have the KSP for this. Let me slide it up. The KSP for lead sulfate is defined as the concentration of lead +2. Oops, that should have been a +2 up there. And the concentration of sulfate -2 divided by the concentration of lead sulfate, which is a solid, so it's 1. We learned that in freshman chemistry. And so I can just plug and chug in here. The KSP is 6.3 times 10 to the -7th, and that equal x for lead. So I get an x here, and 0.10 plus x for the sulfate. And I'm going to do our assumption. I'm going to assume 0.100 plus x is approximately equal to 0.100. Okay, if I do this, this becomes really easy to solve. 6.3 times 10 to the -7th equal x times 0.1. And so x equal 6.3 times 10 to the -6. And therefore 0.100 plus x is equal to 0.100 plus 6.3 times 10 to the -6. Clearly my assumption is good. It is good. And that's how you solve these. Now these can get very, very complicated. I'm going to do one that's slightly more complicated here in a second. Okay, so it turns out that x is equal to the solubility of lead sulfate. It's also equal to the concentration of lead +2 in the solution. The concentration of sulfate is equal to 0.100 plus x, which is equal to 0.100. So in a problem, I could ask you for any one of these. I could ask you for the solubility. I could ask you for a concentration. Okay, you have to read the questions. All right, let's do a more complex problem. Okay, here's my second problem. What is the concentration of mercury 2+2 in a saturated solution of mercury chloride that is also 0.20 molar calcium chloride? So this is it's the same problem, but a little bit more complex. I want to go through it pretty quickly with you. All right, so the first thing I need to do is think about what all I have in solution. And we have mercury chloride and calcium chloride. Now, there's a couple things here. I should recognize that calcium chloride is a soluble salt. If I don't, there's other hints. If I make a solution 0.20 molar, that means it had to have dissolved. So the 0.20 molar here implies that it all dissolved. Note, I didn't say anything about the concentration up here because I don't know it. That's what saturated means. It means there's as much in solution as possible, and I don't know what that is. So my reactions then, I have two reactions. I'll consider the mercury chloride first, Hg2Cl2 in equilibrium with mercury 2+2 plus 2 chloride minuses. Don't be confused over this mercury 2+2 ion. It's a strange ion that we get. Mercury dimerizes. Okay, so that reaction's an equilibrium reaction, and the other one is non-equilibrium. It's calcium chloride. It's a 100% reaction. Goes to calcium +2 plus 2 Cl minus. Notice I'm not putting states on these. If you don't know states or you're unfamiliar with them, put them in. I'll put them in this time. This over here is a solid, aqueous. So if you don't understand those states, ask in class. It's important. So over here I have an ice table. And on this side I have an if table. And I said it was 0.20 molar, 0 minus 0.20 molar plus 0.20 molar and plus 0.40 molar because I have a 2-to-1 ratio here, 2-to-1. So be careful with that. So my final concentrations in here are 0 molar, 0.20 molar, and 0.40 molar. Now I can plug into here anything that fits. The chloride is in both reactions. It's common to both, here and here. So when I look at this, I have dash 0, and I have 0.4 molar from the calcium chloride reaction. And so the change is minus x plus 2x, don't mess that up, and I get x and 0.40 molar plus 2x. Now, the KSP equation, KSP is equal to the concentration of mercury 2+2 times concentration of chloride squared divided by the concentration of mercury 2 chloride. Mercury 2+2 chloride. Okay, so this is 1, of course, and so my KSP, which is given, I can look that up. The KSP for this is 1.2 times 10 to the minus 18th, and that equal x times the chloride concentration is 0.40 plus 2x, quantity squared, So when I solve that, I end up with, up here, x equal 7.5 times 10 to the minus 18th, which is equal to the concentration of mercury 2 plus 2. In this case, it's also the solubility of the mercury chloride, but I didn't ask for that. So read your questions carefully on it. Okay? Now, I picked some nice problems here. Our assumption was good. When I solved this, I didn't explicitly state it, but I assumed 0.40 plus 2x was about 0.40, and this is, it's good. 0.40 plus 2 times 7.5 times 10 to the minus 18th is equal to 0.40. You can try it in your calculator. Works out every time. Okay, so the assumption was good, and I should have stated that. It's so good I didn't even think about it. You do need to state them on problems that you do on exams. All right, that's it.